So, hello Year 11 and welcome to this, the fourth video in the series looking at those skills from GCSE that many students never really master and then come to bite them back when you get to A-level. And today we're going to have a look at energetics. Now this came in, if you did the AQA course, as C5, where you looked at endothermic and exothermic reactions and bond energy calculations. And many students can do those without really understanding the details, and that does come back to cause some problems at A-level. So even if you manage to do bond energy calculations, you've got to ask yourself, did you really understand what was going on during those, or were you just following a procedure to answer them? And possibly the first thing I can do is I can ask you about this. Which of these diagrams shows an exothermic reaction? You should recognise these as energy level diagrams. We've got the progress of the reaction, or what's sometimes called the reaction coordinate, on the bottom, energy on the y-axis. Which of these shows an exothermic reaction? Then explain your answer. Pause the video and have a think. Okay, well, what many students do is they would say something like this. Oh, right, these chemicals, they are absorbing the energy and so they must be getting hotter. This must be the exothermic reaction. These chemicals, though, they are losing energy, so they're getting colder. This must be the endothermic reaction. But this is completely and totally wrong. Wrong. It's shown that you don't really understand what these diagrams are meaning. Actually, what this is the chemical energy. So what we have here on the side shows the chemical energy of the system, of the reaction that's going on. And if the reactants are gaining chemical energy, then that means that the energy's got to be coming in from somewhere else. So it must be absorbing energy. Now this energy can be light, for example photosynthesis. It can be electrical, for example electrolysis, or more commonly it is heat. And if it is absorbing heat energy, this means that there is less heat energy. So it's getting colder. Also, because the energy is going in, heat energy is going in, endometrium, thermic, heat going in, endothermic. That's an endothermic reaction. Here, though, the reactants have lost chemical energy as they become to the product. Well, that energy has to go somewhere, and so it must be releasing energy. And again, this can be as light, glow sticks. It can be as electrical, in a battery, or most commonly it can be heat energy as in combustion. The energy is going out, exoskeleton, thermic. This is an exothermic reaction. Because there is more heat energy, it is getting hotter. And that is the first misconception that many of my students, I would say over half of my Year 12 students, the first time they revisit these ideas, have got that the wrong way around. Over half. And remember, these are all students who got 7s, 8s and 9s at GCSE. As we move forwards, you will find that we don't really use the term energy anymore, because energy is a bit too unspecific. We use the term enthalpy. and we give that the letter H. And that just very specifically means chemical energy, or even more specifically, bond energy. It's the energy stored in the bonds, and we give it the symbol H. So there you go, enthalpy. So if we are going from a situation where there is low enthalpy to a situation where there is high enthalpy, our value of H has increased. In other words, delta H, the change in bond enthalpy, is positive. And remember, this is an endothermic reaction. If here we start off with a lot of H, we end up with less H, well, therefore the change, as in it says up here, delta means the change in, and you're going to have to get used to that. So delta means the change in. So delta H, the change in enthalpy, is negative. We lose enthalpy, and this is an exothermic reaction. And you do need to instantly be able to associate these signs. Negative means exothermic, positive means endothermic. So to summarise here, if we got an endothermic reaction, delta H is positive, heat is taken in, and the products have more chemical energy, more bond energy than the reactants. For an exothermic reaction, delta H is negative, heat is given out, the products have less bond energy than the reactants. Okay, here's the second common misconception. If asked to explain something like why is a reaction exothermic, students will often say, the energy needed to make new bonds is less than the energy needed to break the bonds. And so that means that you don't need to use as much energy making the new bonds as you need to break the bonds, so there's some energy left over. The real problem here, the real misconception, the horrible thing, energy needed to make new bonds. There is no energy needed to make new bonds. In fact, energy is released when forming bonds. And it goes against what we think naturally. You know, if you want to make a cake or make a house or make something, it takes energy. But actually, for chemistry, for making bonds, energy is released. A better thing to think about is magnets. If you think about going up to the biology gate and trying to open that biology gate without having the password, it takes a lot of energy trying to pull those gates open. It takes effort to pull magnets apart. The bigger the magnet, the more energy it takes. You've got to put in energy in order to separate magnets. But magnets jump together by themselves. You probably know that if you've got two magnets on a desk and they're facing so that the North Pole is near the South Pole, then these two magnets will automatically jump together, letting out energy as sound. So the magnets will naturally jump together, releasing sound energy. And this poor gentleman here, man gets his genitals clamped between magnets during health therapy and has to have call firemen to have them removed. This gentleman found out, to his own detriment, that two very powerful magnets will slam together with no input of energy. In fact, probably there was a large release of energy as these things did jump together. But it certainly took energy, and it took firefighters and medics to separate those. So the same is true of atoms. It takes energy to separate atoms, always takes energy to separate atoms. So if we want to break these bonds here, we have to put energy in. But if atoms come back together and form bonds, energy is always released. So as these bonds form, they release energy, okay? So how does this relate to exothermic and endothermic reactions? Okay, just think about every part of this. An exothermic chemical reaction, this is one that releases heat, is a chemical reaction where the products have less energy, less enthalpy, than the reactants. This is because more energy is released forming bonds than is taken in to break bonds. So we need to break the bonds at the start to separate the atoms, so from the reactants to atoms, but then when they rearrange to form the products, more energy is released. And therefore, we've got some extra energy here, delta H, which is negative, and this bit of energy is what is released. Because there's extra heat energy, the temperature goes up, gets hot. And because it's hot, energy is given out to the surroundings, okay? You can think of a radiator, can't you, on the wall of your room. And because it's hot, it's releasing energy to the surroundings, to your bedroom. Okay, so the temperature goes up and then energy is given out. So temperature change first, then energy released. Again, think about endothermic reactions. I'm going to just change the title there. Endothermic reactions. An endothermic reaction, so one that absorbs heat, is one where the products have more energy than the reactants. This is because more energy is taken in to break the bonds than is released when new bonds are formed, okay? And again, we've got this bit of energy, only this time, this is the extra energy that is needed to go from reactants to products rather than the energy released, the extra energy released. Because it needs energy putting in, the temperature of the system goes down, gets cold. And because it's cold, energy is taken in from the surroundings. So think about your nice ice cream. Okay? Hopefully none of you think that an ice cream releases cold. What it does is an ice cream absorbs heat energy so it melts. And again, it gets cold first, then it absorbs heat. Okay, the temperature change comes first, the movement of energy with the surroundings comes second. Some examples, fireworks, of course, classic exothermic reactions, combustion, every form of combustion, releasing heat energy, exothermic reactions. Fireflies, another version of an exothermic reaction, only this time releasing light. Endothermic reactions, for those of you who like sherbets, anything like that, that's an example of a chemical reaction that needs to take in energy because the products have more energy than the reactants. More chemical energy, more enthalpy. So therefore your mouth gets cold, or sorry, well, therefore the sweets get cold, and because the sweets get cold, they then suck energy in from your mouth, and so your mouth gets cold. Electrolysis, again, an example of an endothermic reaction. Doesn't go by itself, you need to constantly supply the current. Why is that? Well, the products have more energy, more chemical energy, more enthalpy than the reactants. So it is taking in electrical energy. The other major part of that topic was calculating bond enthalpies. And despite how many times I said to year 10 and 11 students, draw out all the bonds, and no matter how many times I say to year 12 students, draw out the bonds, lots of students still choose to ignore that, and consequently they miss bonds, or they mislabel the bonds. So here's a combustion reaction, methane and oxygen forming carbon dioxide and water. First thing to always do, I would always say, just draw the things, all of them. You've got one methane molecule, two oxygens, two CO2s, two H2Os. And that means you can tot up the bonds you've got. You've got 4 CH single bonds. You've got 2 OO double bonds. Right? Very important you realise it is not, absolutely not, 4 OO single bonds. Okay? 2 OO double bonds. A double bond is not the same as 2 single bonds. Here, similarly, you've got 2 CO double bonds. You do not, absolutely do not have 4 CO single bonds. They will not give you the same energy because they're not the same. You've also got 1, 2, 3, 4 OH bonds, okay? And if you know the energy of those, you can then tot up how much energy is stored in the bonds of the reactants, how much energy is stored in the bonds of the products. Remember, breaking bonds takes energy. So energy in, and then we have atoms. Always, every bond, there's not a single exception to that rule. Every bond takes energy to break it. Every bond requires energy in, just like magnets taking energy to separate them. Bond breaking is endothermic. Making bonds, here, whenever the bonds form, energy is released. Always, no exceptions. Making bonds always is exothermic, releasing energy. So with a problem like this, you would draw the bonds, you would count them, ticking them off, just as we did. Then you would look up a table of what the bond enthalpies are. And again, you would be very careful because notice here, we have got CO single bonds listed. And we mustn't mistake those for CO double bond. We've got to be really careful that we're choosing the right bonds, especially at A level. You will not, at GCSE, you were given a small number of bonds. At A level, you have a data book, which will have 100 of them. You've got to select the right bonds. So bonds broken, energy needed, total energy that is put in to break the bonds, releasing the energy released when bonds are made, total energy released, so this is the energy out. And instantly, just from our intelligence, we can see that more energy is being released than is being put in, so therefore it's going to be exothermic, it's going to be releasing energy. At GCSE, we probably just said, well, the easiest way to remember it is you do energy in minus energy out, And if you always do that and you keep your reactants on the left and your products on the right, you'll always get the right sign. And again, here we go, energy in minus energy out. At A level, we've got to be able to think about this in a little more detail. Why do we do in minus out? Here's one for you to have a go. Convince yourself that you can do them. It should be very quick. What is the energy change for the reaction that occurs in a fuel cell? Go. Right, well, I'm very much hoping that you realise that the energy in was going to be 1370, energy released 1856, energy needed to break the bonds minus energy released forming new bonds, minus 486 kilojoules per mole. It should really be, because these are kilojoules per mole. Now, I'm hoping you all realise it should be a negative number. It's a fuel cell. It's used to provide energy, and therefore it is going to be exothermic, releasing energy from the chemicals. And so if you've got a positive number, I really hope you thought, hang on, I've done something wrong here. At A level, you certainly need to be able to do that so that you can tell if you've made a mistake. Delta H is negative, reaction is exothermic. Here's another example. This is propane combusting. Propane and oxygen form carbon dioxide and water. Calculate the calculate the enthalpy change of this reaction. Well, I hope you got that the energy in 6522. If not, did you forget about the carbon-carbon bonds? And if you did you draw out those molecules first? Energy released 6912, overall therefore in minus out minus 390 kilojoules per mole. The reaction is exothermic. Okay, a reminder, it always takes energy to turn the atoms. This is Frey. I was a huge fan of Joss Whedon and Buffy the Vampire Slayer when I was younger, and one of his other creations was Frey, this futuristic slayer. So ray gun there, splitting up the atoms. Bond dissociation energies always give the energy taken in to atomize the chemicals. The atoms are always higher in energy than the reactants or products. You need to know that. When you atomize these things, it's always high energy. Doesn't matter whether you are turning the reactants into atoms or whether you are turning the products into atoms. You can guess what else I was a fan of. It always takes energy. So, an analogy I often use when I start with year 12 is, imagine you've got two villages who live on opposite sides of a mountain. You've got village 1 and village 2 here. And they want to know which village is higher. It's a matter of pride. Who lives higher up the mountain? Obviously they can't see each other because they're on opposite sides of the mountain. And it'd be very difficult to work out how much higher they were by going around the mountain. But what they can both do is they can both see this reference point here at the top of the mountain. So we've got this reference point up here. Now, the village on the left knows that to walk to the top of the mountain, they have to walk up 750 steps to go to the top of the mountain. On the right hand side, they have to go up 800 steps to get to the top of the mountain. So let's imagine a person here. As they walk up, they go up 750 steps. But then they come down the mountain. They go in the opposite direction to walking to the top. So they go in the opposite direction of this number, minus 800 steps. They're going against this arrow. This arrow told us how many steps it took to go up to the top. They're going against it. So that's why we flip the sign, minus 800 steps. And that obviously gives us minus 50 steps. Telling us that for someone going from the left village to the right village, they go down by 50 steps. This may seem obvious, this may seem ridiculous, but trust me, when you have numbers that might be plus or minus, and you're going with the arrows or against the arrows, being this rigorous is really important. So let's have a look here. It's the same idea. This village is obviously our reactance, and we know how much energy is needed. So these are the bond energies. We know how much energy is needed to atomize the reactants and go up to this reference point here. We also know the bond energies of the products and how much energy is needed to turn the products into atoms. So if we're going from the reactants to the products, we put in the bond energies of the reactants, we go with this, but then we're going in the opposite direction to the bond energies of the products. The bond energies are the energies needed to atomize, but we're putting the atoms back together. And therefore, we go in the opposite direction of the bond energies of the products. So our overall energy change is the bond energies of the reactants minus the bond energies of the products. So in chemistry, we look up to a reference energy level. When all bonds are broken and all atoms have been separated, and going up from the reactants to those atoms or going up from the products to those reactants, both cases takes energy. We can turn these ideas into a cycle. Here we go. So in this example, we've got the reactants, sulfur dioxide and hydrogen sulfide. And if we sum up the bond energies of the reactants, we get atoms. We get 3 sulfur gas atoms, 2 oxygen gas atoms, 4 hydrogen gas atoms. And this is really unusual because we spend most of Key Stage 3 and most of GCSE telling you it's O2, it's H2. These things are diatomic. Normally, yes. But we are atomizing. The whole idea of a bond energy is that we are splitting all the bonds. We are splitting everything into atoms. We can take those same atoms but in a different form. So here we've got sulfur and we've got water, and again, if we split up those products, we will end up with the same gaseous atoms. So going from reactants to products, we go with this arrow, so that's why that's a positive number here, but we go against this arrow. Instead of pulling all the atoms apart, we are putting everything back together, and that's why that is negative, that number. So here's an example of an A-level bond energy cycle. Carbon monoxide and water, carbon dioxide and hydrogen. We want to know that value there, delta H. What is the enthalpy change of this reaction? Well, we can imagine, as you would do at GCSE, pulling everything apart into atoms. We've just got to do it more formally. You would pull it apart into a carbon atom, 2 oxygen atoms, 2 hydrogen atoms. To work out the enthalpy change there, well, we're going with this arrow, so plus 1077. We're going with this arrow, which is 2 H2O bonds, so plus 2 times plus 464. That's the energy that is being put in to atomize everything. But then we are going against this arrow. So it is minus plus 436. And we are going against this arrow as we put 2 carbon dioxide bonds back together. So again, minus 2 times plus 805. And if you do the maths there, you will hopefully, unless I've done my maths wrong, end up with minus 41 kilojoules per mole. In other words, this is exothermic slightly. Energy in minus energy out. This is an actual A-level question. So you're given some bond energies. You've got to complete the cycle, then calculate Z, and hence calculate the enthalpy change of the reaction. So firstly, when we are atomizing stuff, when we are using bond energies, we always form gases. So that state symbol is a gas. On the right, we've got 6, 7, 8, 9, 10 oxygen atoms. So that must be 10 oxygen gas. So that means it's 5O2 gas there. So propane and 5O2, 3CO2, 4H2O. Right, Z. Well, let's draw it out, okay? So we've got 3 CO2. So we've got 6 CO bonds, 6 times CO, 6 times 805. We've got 4 H2O. So 1, 2, 3, 4, 5, 6, 7, 8. 8 times 464 because it's 8 times OH. And if you sum that up, that's what Z is. 6 times 805 plus 8 times 464 equals 8542. So that is plus 8542 kilojoules per mole. Remember, bond dissociation energy is always positive. Now we need to work out what delta HX is. So we go with this arrow. So plus 6490. Then we're going against this arrow because we're putting stuff back together rather than pulling it apart. Minus plus 8542. So 6490 minus 8542 is minus 2052 kilojoules per mole. So there you go, an A-level question. Here's 3 for you to have a think about. Some mean bond enthalpy values are given in the table below. Consider the following bond enthalpies. Multiple choice. You'd have about a minute for each of these questions. So why don't you go away, have a think, and then rejoin the video. Okay, so as we are going from hydrogen and iodine to atoms, we are going with the arrow. We are breaking part 1 hydrogen bond, 1 iodine part. So that should be plus 436 plus 151. Okay, so already B and D are not looking good. Then from atoms to hydrogen iodide, we are putting together two HI molecules. So we're going in the opposite direction from the bond dissociation energy. So minus 2 times plus 299. So that matches C, minus 11 kilojoules per mole. Here, again, what we're doing, well, we're breaking two OH bonds and one OO bond. So therefore, this is the energy in. There's 146 and there's two lots of 463. And that's the energy in. That's all positive. And then we are putting together these atoms. So we're releasing energy. We're going in the opposite direction. So it's minus whatever's in this bracket, which is, again, two lots of 463 and half an O2. Okay, so that is half times 496. I'm just going to take the shortcut, which is that they're the same. So essentially it's 146 minus half of 496. Which gives minus 102 kilojoules per mole. There we go, A. And calculate the enthalpy change for that reaction. I'm just going to leave you to do that. Right. Now, the reason we made that so formal is because at A level you don't just do bond dissociation energies. There are other values you need to be able to use and understand. And I'm going to show you one of these, which is enthalpies of formation. There are countless others: enthalpies of hydration, solvation, neutralization, combustion. Okay, I'm going to show you one example, but it might explain why we need to be so formal with the bond dissociation energies. The enthalpy change of formation is the enthalpy change that takes place when 1 mole of a compound is formed from elements in their standard states under standard conditions. Okay, so if we're talking about forming water, liquid water, we would talk about forming that from a hydrogen gas molecule element standard state. The standard state of hydrogen is a gas, H2, diatomic. And we would form it from half a molecule of oxygen. Again, oxygen, standard state of oxygen is a gas, a diatomic gas at room temperature. And so forming water, we would take 1 molecule of hydrogen gas, half a molecule of oxygen gas to form water, and the enthalpy change of that reaction would be minus 286 kilojoules per mole. We always talk about forming 1 mole of a substance, so we need to make every other thing, every other stoichiometric coefficient, every other big number, so that we form 1 mole of product. Okay, you might not be used to halves from GCSE. We use them all the time, or even eighths at A level. So here is an example, and you should recognise that it's fairly similar to the bond energy cycle. The reaction we're really interested in is here along the top. So we take ethene and hydrochloric acid and we form chloroethane. And that's what we want to know. What is the enthalpy change of that reaction? Well, instead of pulling everything apart, we can imagine making all of these from a standard Lego kit. Carbon, hydrogen, chlorine, standard states. Carbon is a solid in its standard state. Hydrogen is a diatomic gas. Chlorine is a diatomic gas. We would use the same kits to make both of these. So whether we're making the reactants or the products, we would be using the same stuff. We'd be using 2 carbon atoms, 2.5 hydrogen molecules and half a chlorine molecule. Now, just like with the bond dissociation energy, we imagine going from the reactants to this common state, to this reference state, and then back again. But the difference here is now we are going against the arrows in the first part. So what this is saying is making the reactants from our standard kits would take 52.2 plus minus 92.3 kilojoules of energy. But we are not doing that. We are taking the reactants and we're disassembling them and putting our standard kits back together. We're taking our Lego blocks apart and putting them back in the box. So we start by going against these arrows. So minus plus 52.2 minus 92.3, okay? And this is why we've got to be careful. We've got a minus minus here. We are going against that arrow, so it's going to become a plus. But then we are going with this arrow. So that is plus whatever that value is. But oh no, that's a minus. So we've got a minus plus, a minus minus, and a plus minus. And this is where students fall apart. They are not rigorous. They don't know how to be rigorous. They've never had to be rigorous. They've just kind of done it by whim and by a feel or by knowing what the right answer should be. Now you will come unstuck if you're not rigorous. So the answer to this, the actual enthalpy change of this, is minus 52.2. Because we're going against that arrow. Minus minus, so plus 92.3. And then we're going with the minus 109, so minus 109, which gives us an overall answer of minus 68.9 kilojoules per mole. We could have done this from bond energy data, but actually formation data is much more specific. Bond energy data is an average. It gives you mean bond energies. It's great if you want a sort of hand-wavy, rough answer. But if you really want to calculate precisely the enthalpy change of a reaction, then formation data such as this is the way forwards. So here's an example, again an A-level example. Fill in, finish the cycle, then calculate the enthalpy of combustion of methanol. Right, well what would we need? Well, I can see that there's one carbon, so I need a carbon and its standard state is a solid. On each side I've got 4 oxygen, so I'm going to need 4 oxygen atoms. Well, the standard state of oxygen is an O2, so plus 2 O2 gas. These are not bond dissociation enthalpies, right? Get this sorted in your head. There's lots of types of cycle. Here we are doing what's called a formation cycle. We are imagining building this from elements rather than pulling things apart into atoms. And there's some students who never get this. They just genuinely can't get their head around what we're using, what we're doing, why we're doing it. But here I'm told it's formation data, delta HF, so I know that my toolkit is elements. We've also got 4 hydrogen atoms on each side, so I'm going to need 2 H2 gas. Right. Making ethanol. So coming up here, that is minus 239.1. Making 1.5 oxygens. Right, well, here's the thing. That's going to be 0. Because oxygen, turning it into oxygen, there's no energy change. Oxygen is oxygen. So if I'm making an element from an element, there's no energy change associated with that. Coming up here, I'm making a CO2, which is minus 393.5, and I'm making 2 waters. This tells me how much energy is needed to make 1 water, so that is 2 times minus 285.8. So if I want to know the enthalpy change of this reaction going from there to there, I'm going against these arrows. So minus 239.1, and I'm going with these arrows. So plus minus 393.5 plus 2 times minus 285.8. And if I put all that into my calculator, hopefully the answer to that is minus 726 kilojoules per mole. It's very similar to a bond energy cycle, but the arrows are going in the opposite direction. Instead of going from the reactants and products, so for bond energies, we go from the reactants and products to atoms, whereas for formation, we talk about making the reactants and products from elements. And therefore what you'll notice for this one is instead of doing reactants minus products, we are actually doing products minus reactants. If you want to, here's 3 examples for you to try, and I'm going to flash up the answers, so if you don't want to know, pause now. That's the answers. And here's just an example of some of the 1-mark questions that you might be given. So let's have a look at 30. Given the following data, select the expression which identifies the enthalpy change for this reaction. Well, we can imagine making these things from oxygen and iron. So we would need 1.5 O2 gas and 2 Fe solid, and we can make each of those from that. Well, making this would be 2 times the enthalpy of combustion of enthalpy of formation of FeO and 0. So that would be there. And this one would be just 1 times the enthalpy of formation of iron 3 oxide. And to go from there to there, we go against that arrow. So that would be minus 2 times minus 270. And then we would go with this arrow. So that would be plus minus 820 to go there. So the answer would hopefully be something in the order of minus 820 minus minus plus 2 times 270, and that matches C there. Okay, and you will get faster at these, you will start to understand these, but that is an example, and you've got a minute to just work that out. In summary, and I'm only showing you 2, remember there's going to be lots more cycles thrown at you at A level, or AS level, and then A level. But in summary, with bond enthalpy data, we are pulling these apart to make atoms. The arrows go away from the reactants and products. And therefore, if we're doing this, we are going with the reactants and we're going away from the products. So it's reactants minus products. For formation data, we're talking about making these things from elements. So if we're going from the reactants to the products here, we are going against the reactants and we're going with the product arrows. In other words, it's products minus reactants. And this is why you've got to start being good with your definitions. You need to know what the things mean. You need to start being able to draw these cycles that we've looked at, and you need to be good and rigorous with your maths so that you don't confuse a minus minus for a plus minus. I'm not intending that you understood all this. I'm not intending that you can do this, but I am trying to show you where your knowledge from GCSE is going. See you in 2 weeks.